So I'd like to split this talk up into the sections that are shown here on this first slide. So first of all, I wanted to say something about the role of yeast. I then wanted in the next section to go on and say why it is that I think that we need better methods for measuring yeast concentration and how that can be done using this Aber yeast monitor. And then a section just talking about the ways that this piece of equipment can in fact be used, and then a few words to draw everything up at the end. So just to start off and just to say some words about the role of yeast. And I think it's fairly clear. I think that yeast is obviously the brewery's most precious. It's the brewery's most precious asset. It obviously is the yeast that actually converts wort into beer. And you can clearly split that up into some of the aspects that are shown here on this slide. So obviously it has got a key impact in terms of process efficiency, so that you want to convert clearly as much extract into beer as you can. It's got a really big role in terms of the way that the plant itself is actually used and the plant output. So you can look at things like fermentation at cycle times, and that can be viewed obviously, that can be viewed purely in terms of length, but also in terms of consistency. And then obviously the yeast has got a very big role in terms of final beer flavour. So a great deal there that you need to actually get right. So if you look at the things that you need to get right in terms of yeast and what you need to do with it, well, it obviously follows that you've actually got to have the right strain, and that strain needs to be pure. It needs to have a very high viability, and the final point is that you need to be able to accurately measure the viable yeast concentration, and it's obviously that last point on this slide here that I'm actually going to be dealing with. So if you look at some of the primary yeast operations that you need to carry out during the brewing process, and those are kind of listed here on this slide, so that you need to obviously to have the correct quantity of yeast for pitching, and you need to be able to control the actual pitching rate. During the fermentation you need to grow yeast, and typically the rule of thumb was that for every FV that you pitch you can crop 2. So you want to possibly grow between 3 and 4 times more yeast every time. But obviously you don't want to grow too much yeast, because more yeast growth in essence means a lower yield in terms of beer. At some point during the process you need to separate the yeast crop, so that you need to be able to control that in some way. That yeast is going to be cropped, is going to be put into storage vessel, so that you probably want to know what's happening to the yeast whilst it's held in that period in the interval between cropping and re-pitching. So if we look at the methods that are still often used for measuring yeast mass, and those are shown here obviously on this slide, and you can split those up into either offline or online methods. So the offline method is the take a sample and work out the amount of SPUN solids that's present within a yeast slurry. So you take a known weight or volume of yeast slurry, centrifuge it, and from that you can work out how much yeast there is in there. There are various types of particle counter that you can use, or the one that I guess which is most often used, and which is the one that's shown here on this slide, is that you carry out an actual count, SL count. By using the right type of dye, you can in fact measure total yeast counts and viable yeast counts. Methods that can be used online in general are based upon light scattering. if we look at some of the aspects of those methods and consider their shortcomings, those are kind of summed up on this slide here. So that if you're going to carry out visual cell counts, you probably need a reasonably skilled person who can actually carry that out. The methods tend to take quite a long period of time. And obviously there is an issue that once you take a yeast sample from a large mass of yeast slurry present within a large storage tank, there's always the question of whether you're really getting an actual representative sample. When you carry out visual counts, it always involves a very large error. So those methods are generally not very good. On the other hand, if you look at the online methods that are used, since these are in effect just based upon light scattering, clearly they will actually measure the presence of any particles that are present within the operating field. So they will not actually correct for dead cells. They're not actually correct for non-yeast solids that might also be present. You may have even more problems if you have yeast strains that may form very large flocks or may even possibly grow in the form of chains. So looking at those methods as a whole, it's clear that all of them have really got quite marked, quite big shortcomings. I think it's just interesting then, in order to set that into context, and I just thought it would be quite good to actually show some data which dates back to the early 1990s. And in this case I'm just going to show you a couple of graphs, and these are actually cycle time data for 1500 hectoliter FVs. So these are the mean cycle times that were, or these are the actual cycle times, I should say, for each of those vessels within the tank farm. So shown on the first graph here, as you can see. So this is from vessel 25 up to number 44 as a function of time. And in this case it's showing you the time to reach final gravity. And the sample size was 272. And clearly, if you look at the data shown on this slide, you can see that there was a really incredible large amount of spread. So if you consider that situation there, very difficult to plan, very difficult to know when the actual fermentation will end, clearly a lot of problems. And that you would also probably expect that with that amount of variability, it's likely to lead to variability elsewhere. So probably also in terms of things like yeast growth, crop sizes, and by inference, beer yields, and also the beer quality. If you look at time to VDK spec, which is shown on this slide, so these are the actual VDK stand times. Again, an incredibly wide range. So that was where we were in about 1990, and we obviously realized that we really needed to do something about this, and that we thought that one of the major errors that we had was simply that we just couldn't actually control the yeast pitching rate. And we had reasons to think at that time that if we could do something about pitching rate, it's likely that we could cut down this very wide range that I've shown here. If you consider what's happened since that time up to where we are at the moment, there are various trends which are indicated on this slide. So that something that's happened, clearly fewer and larger breweries, and typically breweries that might have to handle several different yeast strains. You may have very, very large batch sizes and typically using extremely concentrated worts. And in order to shorten cycle times, a general increase in terms of the fermentation temperatures. So all of those things have happened, and set against that, on the other side, you actually need to manage that process using fewer and fewer people. There may be I put in there a question mark on this slide, but possibly fewer people and maybe people that are less skilled. And clearly one of the things, therefore, that happens in that situation is that it makes sense, if you can, to carry out more measurements in line or in tank and use that as the basis of automatic processes. So that kind of timeline fits in really with this piece of kit being introduced into large-scale brewing. So if you actually think about the consequences of those various trends, well, those are indicated here. So generally, very large batch sizes, increases in temperature, very concentrated worts, generally increased levels of yeast stress, and as a consequence of that, fewer serial re-pitchings. So when commonly you might be re-pitching, say, between 20, 25, 30 times, these days it's actually common that you might not be able to re-pitch more than 4 or 5 times. And clearly that increases all sorts of pressures in terms of what you can do with yeast. It certainly obviously leads to an increase in pressure on things like propagation plant. And in order to manage that process, I think it's fairly obvious that you need to have it underpinned by very accurate methods, and preferably methods that you can use in line. Well, I think since that time that we knew, when I showed you those graphs that date back to 1990, that we also were not probably very good at being able to control total extract going into FV. We were not very good at being able to control giving a known dose of oxygen. Fermentation temperature maybe not all that bad, but certainly since that time methods have been put in place whereby we can now accurately measure and control all of those factors. However, really what we didn't have was a good, accurate method of measuring yeast concentration in line. That obviously follows neatly on to the Aber yeast monitor. And just prior to showing what it will do, I just thought I'd say a few words about the way that it works. Well, the first point shown on this slide is, I guess, the one which is key. It gives an instantaneous measure of viable yeast concentration. And I think that the two key words are instantaneous and viable. And how in fact does it do this? It's actually based upon the dielectric properties of living cells when they're in a medium which contains charge groups such as wort or beer. If you consider that you have such a liquid which contains charge groups, and if you apply a field as shown, then obviously those charge groups will actually tend to migrate towards the anode or the cathode depending on their charge. So fairly simply, if you put some yeast cells into that field, well, the feature of yeast cells and other cells is that they are surrounded by a non-conducting layer, which is actually the membrane. And because this has this non-conducting layer, then those yeast cells are able to function as capacitors. So they will build up a charge, as shown, and it's possible to measure that charge. And that is the actual basis of the way that the instrument works. So that the yeast cells within the operating field function as capacitors, And that measures, that's something that you can look at, you can actually measure, and it is a direct function of the total biovolume within the operating field of the instrument. And you can convert that then obviously to recognize yeast concentration units that we would normally know in terms of brewing. So viable spun solids or viable cell counts per unit volume or mass. If you have a dead yeast cell, so this would say be a cell that would score as being non-viable using a standard vital stain, then those cells have actually got ruptured or non-functional membranes. And because the membrane is not functional, then they're not able to build up this charge, and therefore there is nothing to measure. So as far as the instrument's concerned, dead cells are not actually there. So hence the reason that it only gives you a reading with viable yeast cells. And you can use exactly the same reasoning and logic for the presence of things like trub and gas bubbles, that because they're also not able to build up this charge, they do not cause any interference. So if we look at it in a way that I guess is simple brewers that we might actually more often think of, if you have a sample of yeast slurry, as shown here, and obviously the sample of yeast slurry consists of liquid, a certain amount of beer, it consists of cells, some of which will be living and some which are not, and a certain amount of trub and so on. And the Aber biomass monitor only gives you the reading that's equivalent to the viable spun solids fraction. So you can summarize that by saying that the instrument gives an instantaneous measure of capacitance that's a function of the intact yeast cells that are present within the operating field. And you can relate that to normal yeast concentration units, and you can choose whichever that you wish. So they can be spun solids, it can be viable cells per mil, and so on. You don't get any impact from dead cells. That's something that you need to bear in mind, of course, is that it only measures the viable fraction. So the instrument comes in both benchtop and inline versions. So you can clearly use the benchtop version in the same way that you would if you went to your yeast storage vessels, took a sample of yeast, took it back into the lab, measured the viable yeast concentration, calculated things like the pitching rates from that. Or obviously you can use it inline, which is mainly what I will actually be talking about. You can obviously use it for other things if you wished. So for example, you've got an option for mounting one of these probes into a yeast propagator, and you can obviously look at yeast, you can look at the way that the yeast grows and concentration of that yeast within such a growth vessel. It has a very wide range of operation. So certainly up to 5 × 10⁹ viable cells per mil, which is equivalent to something like 70% viable spun solids. So it's obviously suitable for measuring viable yeast concentration in, for example, concentrated pitching yeast slurries or cropped yeast. Because it has this wide operating range, if you use the lab-based monitor, then you don't need to dilute the yeast sample, which is obviously an obvious source of error. Okay, so what things can you use it for, and how well does it work? Well, the most obvious way that you would use the instrument is obviously to control pitching rate in line. And a pitching rate control system would look something like this. So shown along the bottom, you have the main that's carrying the wort from the paraflow into the FV. And as is normal practice, you have yeast within a storage vessel that's been pitched into that wort as it moves into the FV. So if you put one of the yeast monitors into the yeast pitching main, then the yeast monitor gives you the viable yeast concentration at that point that the yeast is passing the probe. If you then take the output from that, and the output from a flow meter, or it could be a load cell on the yeast unit storage vessel itself, clearly using those two outputs, you can calculate the total viable yeast mass, or the total viable count that's past the actual probe. So as long as you know the volume of wort, once you've reached the set point, then you can feed back and switch off the pitching valve, switch off the pitching pump and so on, and therefore obviously use that to control the yeast pitching rate. So how well does that work in practice? This is some work that we did when we put one of those systems in place. And here you can see the standard deviation in cycle time. So this is the mean standard deviation in cycle time for a tank farm of 28 FVs. And it was at month 12 that the new pitching rate system was actually put in place. So prior to that time, months 1 up to 11, the pitching rate control at that point was based on offline sampling and spun solids. And you can see that as soon as the Aber system was actually put into practice, there was a step change in terms of fermentation consistency. It obviously follows that you can use more or less the same system in order to control taking off a yeast crop, and a cropping system would actually look something like this. So in this case, you have the yeast probe mounted in the main where you're taking off the yeast crop, and you measure the viable yeast concentration in line as you take off the yeast crop. If you have a suitable flow meter in line as well, then obviously you can calculate the total mass of yeast that you've taken off the vessel. And depending on how you set up this system, you can direct the liquid flow in any way that you wish. But for example, you could send a fraction off to waste tank, you can save a fraction in a yeast storage vessel, and when you hit the beer yeast interface, then clearly you can direct the process flow, for example as shown here, to a green beer centrifuge. So you can use it to control taking off the yeast crop. And this indeed is some data which shows you outputs during a cropping. So we have the cropping as a function of time, and the blue line shows the total solids during cropping, the purple line is viable solids, and the red line is the reading from the Aber instrument. And I think you can see that they clearly match quite well. And indeed, you can probably see some portions during the cropping when there is actually probably more non-yeast solids present. And clearly you can use that to choose which fraction of the yeast crop that you would actually choose to keep. If you can control both pitching and cropping, it obviously follows that you can use the system as a total yeast management system, because you've got the inputs of how much yeast is being cropped and how much yeast is actually being pitched. So that some of the outputs that it's possible to obtain are shown on this next slide. So for example, obviously that with this system you can keep a record of how much yeast is pitched. You obviously know which yeast strain it is and where it's from and the number of times it's been repitched and so on. You can calculate how much yeast has been cropped, and therefore from that you can calculate at any given time how much yeast you've actually got in storage. If you know how much yeast has been pitched and how much yeast has been cropped, then clearly you can get a rough measure of how much yeast that you've actually grown. Since you would expect that the yeast crop for any given beer type, for any given type of vessel, is not going to change very much, then clearly if anything does change, that's something that you can also look at and something that you can obviously see and pick up. So for example, if you get a sudden change in yeast flocculence, which occasionally happens, you'd expect to see it if you have this system. So the big advantage of that clearly is that if there is any change, you find that out in a very rapid manner. As you know how much yeast is being cropped, you know what the concentration is when it goes into the storage vessel, and you can measure what the concentration is when it comes out, when it's pitched. So that will also give you a measure, has there been any change during the period in which the yeast was actually being stored. So that you can clearly see how you can use this system as this total yeast management system. There's obviously quite a lot of other things that you can do with it. I've just gone through those two, but you might, for example, consider the list of things that are shown here. So clearly you can use it to monitor propagation. If you practice krausening, you can obviously use it to control that. You could, if you wished, put a probe into every FV and monitor yeast growth. You can monitor counts in green beers, and you could, for example, use it to control a centrifuge. If you're making cask condition or bottle condition beers, then clearly you could use it here as well. So basically anywhere where you want to know, measure and control yeast concentration, it would be possible to do it.